So hello, welcome again to a video where somebody was willing to come and talk with us on camera to share with you guys.
Yep.
Would you go ahead and introduce yourself?
I'm David Clark. I'm an assistant professor here at Grand Valley. I teach math. I love teaching calculus, and I want to talk a bit about glasses. So.
All right. You said this is kind of based on a demonstration you do in class.
It is, yeah. So when I'm teaching Calc 1, there's usually a point where we want to talk about how things are changing and want to get intuition for how they can change in sort of a physical situation. And so something I do in class is I'll bring in a handful of glasses, and I drew a few of them here. So like this is kind of a traditional straight-sided just water glass or something.
Okay.
A flask, so like from a chemistry lab.
And you were saying your wife is a chemist?
And my wife is a chemist, so yeah, this is a shape that comes to mind quickly, and we have these things around, right?
Do you seriously?
Yeah, so you have test tube, Erlenmeyer flask, and Martini glass, which we also have around. So,
right.
And you can draw other shapes too. So I'll actually have some of these, bring them into class, and then like a pitcher of water, and I don't even care how much water is in there, but what I care is that I'll pick up the pitcher and I'll pour it into, let's say, this first glass. And I'll pour it, just holding it really steady so that the water just pours in at a nice constant kind of rate.
Okay.
Like it looks like I'm pouring the same amount of water every second. So I'm not like tipping it back and forth and it's changing really fast. Right. And so we watch what happens to the level of the water in the container. So maybe I'm pouring it in kind of slowly, and after a second, the water's just up to there. And then a second later, water's kind of up to there, and then a second later the water's kind of up to there and up to there, and if you watch it, that keeps happening, and I stop, somewhere up here. But the key thing is, in the glass, nothing surprising happens to the water level. I'm pouring it in nice and constant, the water keeps rising nice and evenly, and it's really boring, right? but we would have known that, right? The sides are straight, nothing's going to make the water do anything strange.
Yeah.
But then the interesting thing happens when you pour the water in exactly the same way into a beaker like this, because the sides aren't straight anymore. And so
I'll say that if you were watching this on video, you might even pause it here and think for a second, what would happen if you say you're going to pour it in just kind of slow, steady rate again?
Yep, so nice, slow, steady, just like I did over here. So yeah, it's a good thing. Think about what do you think is going to happen to the level of the water. Right? As I pour it in, how is that level going to change over time? So, okay, after a second, if you compared like this one to that one, I drew it so this one's a little wider. Mm-hmm. So I say, okay, I'm going to pour the same amount that I put in here, and so I'm actually going to draw it a little lower, right? Because the water level wouldn't be quite as high. It gets spread out a little more, I think. Yeah. And then a second later, the beaker is that much narrower, so it's still probably wider than this glass, I guess, it looks like. So I'm going to say, okay, it's going to have gone somewhere up here, well, not quite there, let's say like this, which is, it's just a little more. Right? If this was a little bit, this is just a little bit more. So it's just that much narrower, less space to fit into. But still, probably not as much as it filled right there, right? Because that was that much narrower.
I was going to ask you, why did you adjust down? But because you're thinking about the comparison to this glass.
I was thinking, however wide, like that was the amount that went into this glass in 1 second. This thing, it can't be that deep because this is wider. There's just more water to fit into there. Or I should say, the same amount of water fits into a smaller place.
And I love this kind of qualitative thinking. Mm-hmm. It's not any numbers, but in general how it goes.
It's got to spread out more. Yeah, and this is a nice comparison. Right? We can always go back to sort of the reference right here. Mm-hmm. Okay, so a second later, it's going to be that much deeper. The side's got that much closer. We're getting close to how wide the water glass was. Mm-hmm. And then a second later, okay, we're squeezing it in more and more. And so, like if I shaded in, let's say I shaded in this space. That's the space that filled up in the last second before I stopped. Mm-hmm. Because I was pouring at a nice steady rate, that means I poured the same amount of water in this space as I did right there, but it fit a different shape. And so the top of it rose up a lot farther because there's just less space to fit it into.
Makes sense. So what does that look like, as you're pouring it in? What's the visual effect of that?
Yeah, so the visual effect as the water goes in is it's sort of slow, faster, 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 and at the end, the water comes out really fast, right? Like if I kept pouring right here, and there's a little straight neck like that, like it would fill up the neck really quickly.
Do you think does that have any, I mean, those flasks are so typical in science. Is that part of the reason why they're like that?
That's a really good question. I would actually think it should be the opposite way. Like, you don't want to risk overflowing or anything.
Right,
you
with
know?
chemicals.
With chemicals, yeah. And I need to ask my wife about that one, because, yeah, as a lab safety thing, I don't know. Maybe that's why there is a neck there. So once you notice you've gotten here, and you take that split second to pause, it's still going to keep filling for just that split second, and maybe that's your safety valve.
Yeah.
That actually gets into what happens with this, because this is what I usually do as the last thing. And I say, okay, I'm going to do the same thing I did in these other two. What do you think is going to happen?
Oh, another good pause and predict. Yeah, okay.
So, what do you think is going to happen to the water level? Well, I mean, we kind of knew what happened here. They're similar shapes.
Mm-hmm.
So if I pour this much water into that much space, it's going to cram in there really fast. So it's going to fill up a whole lot of it all at once. I mean, that's the same as that, it's the same as that, the same as that.
Right.
But then a second later, things got wider, there's more space to fit the water into. It's more like, actually we're about at the width of the water glass now, so it slows down. So the speed that the top of the water is rising slows down a lot. And the fun part is, if I set this up correctly, I'll have a pitcher of water that exactly fits this glass, and I can just dump it in there, and everyone starts going, yeah, you're going to overflow, right?
Yeah.
But it goes so slow, right? It's another second later, the water hasn't gone up nearly as much. Another second later, it's gone up even less. There's no danger of me overflowing at all. And as soon as I see that it's about to hit the top, I can just sort of very slowly pull back, and the water's rising so slowly, it's not going to dump at all. So I really like this because, first off, you can think about it visually.
Mm-hmm.
Right? You can think conceptually, like, oh yeah, I kind of know what's going to happen with the level of the water here. But this introduces a really important idea in calculus of how fast is something changing. And so the thing we're looking at here is how fast the top level of the water is changing. And you can be a little more precise by just saying, like, how fast is the depth of the water changing? It's like here, the depth is some number, and it just keeps getting bigger and bigger, but it's getting bigger and bigger, slower and slower.
Right.
Whereas over here, the depth of the water is getting bigger and bigger, but it just keeps getting bigger and bigger at the same rate the whole time.
Mm-hmm. So we've been doing a lot of trying to visualize these changes in a graph. Do you ask your students to then transfer this to a graph at all?
To then draw a picture of it, yeah. So
Okay.
I think the first thing is just to draw directly a picture of how deep the water is at each stage.
Mm-hmm.
And so I sort of did that with the lines here, but we can turn it into a more standard graph.
Okay.
So I wish I'd done this in a few different colors. I'm going to make one graph because I think it's useful to see them all together in one place.
Okay.
So if I made a graph, and I'm going to label it, this is the depth. And this is just going to be time. And I don't know, I was saying seconds, so I'm not going to put ticks on there. I'm just going to go, as time goes on, we're going to draw how deep the water is. So I'm going to start with, this really is the blue one now. I'm going to try to use different colors for them. We'll see.
Okay. I'm going to be disappointed if the margarita's not green.
Not green, not red? You don't want a berry margarita? All right.
Traditionalist, I'm a traditionalist.
Okay, gotcha. So, I mean, at the very beginning, there was no water in there, right? So I think we draw, okay, the depth is 0, there's nothing. And a little while later, there's some water in there, however much. But the really key thing is, okay, that was a little while, maybe 1 second. That's another little while. Same amount of time, so like another second. The water was nice and steadily increasing, right? So it was increasing by the same amount. So if you looked at the picture, you could say, that was where that dot was. Here's where I want to put the next one. We really want to just draw a picture of how much bigger that is than that. That's one way to think about what I'm going to draw here. And however much bigger that was than that one is the same as however much bigger that was than that one. Right? So if you think about this just meaning how much water got added, I've just got to do the same thing. There's how much water got added. It's exactly the same. My little arrow is exactly the same size each time.
That makes sense.
Yeah. So that's a way to think about the amount of change here. Actually, and I want to be really careful. I don't want to make it look like this is doing anything funny. It just went up exactly the same amount.
Okay. So it's going to be slow and steady.
Slow and steady. You know, another second later, I'm starting from this much. I'm going up by the same amount. Same amount right there. And so if I want to, I can connect all of them together. And
well, that's actually meaningful here, right?
Yeah.
Because you are pouring, it's not like you added the chunk of water.
mm-hmm.
You're pouring the water until that amount of time is gone by.
Yeah, absolutely. So I mean, there really is, like, that point really does mean how much water there is halfway in between as it happens.
And half the amount of time you would have put half, the change in height would have been halfway to the full change. Okay.
And so each of these little arrows I drew here, I mean, that's how much the height of the water is changing. It's how much the depth of the water is changing. And every time I drew them, it's exactly the same amount. And for that matter, every time I went over a little ways, that just meant another second passed, right? I was representing the same amount of time. So going this way means 1 second passed, and going that way meant the water changed a little bit, and every time it changed, it was exactly the same.
Well, that's interesting because you're pouring at a steady rate.
Mhm.
Like the change in volume being steady is the same thing as the change in time being steady.
In this case, it is. Yeah. In this case, it is.
Yeah.
And so that's a thing we know a lot about, right? So I'll ask my students, like, what is this thing we just drew? Right? Well, it's a rise over run, or a change in this direction over a change in that direction. We've talked about that kind of thing before, and this is, I think, mathematicians love this moment where you're like, I'm doing this thing that doesn't seem to have anything to do with anything else. And then you try to represent it or draw a picture or whatever, and you go, oh, rise over run, slope. I know that, and you've discovered a connection to something you know about already. And so what we're really just saying is slope just measures how much the volume increased divided by, or sorry, how much the depth increased over time. Yeah, but all this time the volume was changing by just some amount we haven't even talked about yet.
Right.
Which whatever it was nice and steady. Yeah.
We will.
Yeah, that will happen, right? Yeah. But so this is a picture of that nice and steady increase.
Okay.
Let's do it for this one. So I guess I have to make this one red. So something fancy's happening in the beaker here.
Oh, it's a chemical.
It's
reasonable
chemical,
for it to be
yeah.
red.
It's a chemical, all right. So I'm gonna draw the same thing, right? So
Yeah.
I'll say, okay, let's draw the same picture, and we kind of know what happens there, right? Like, you start out with nothing in it, and then the first time we went through, and remember we're drawing the depth, so the depth wasn't very much. So it's like way down there. It's a lot lower than the water glass. And then the next one, so it's the same thing. I'm saying, okay, I had that much water. A second later, I had more. So I'm going to just draw a little arrow going up from it. And so at that point, it's gone just a little bit more. And I've made it like just that far up.
Okay.
So it's kind of hard to see the arrow. I just drew a little tiny arrow, right? It just went up a little bit.
So before you were doing the arrows kind of at the points. So
Oh yeah,
put the arrow
make
here
it,
so we
make
can
it
see
consistent. Yeah, so I did it like just that much.
Okay.
So the main thing being that's a lot shorter than the blue ones.
Yeah, more than your first one, but less than these changes.
Yeah, so yeah, the first one's just a little ways up. That second one is a little bit more up, but still not that much.
Okay.
And then the third one up here somewhere, it's a little bit more up. And we're kind of getting closer to how much the blue one was changing. So I can put a point there, and then as we start getting up here, it's a little bit more. And at that point, we might even be getting, the depth is getting higher, faster. It's a lot bigger than was in the glass.
Which doesn't mean you're caught up to the height you were before.
Not
just
at
that the
all.
change in that step.
Yeah, that one little bit is a big change, but it's starting from something that was a lot lower than it was before. Maybe that's pretty close. And then up here somewhere, like that would be when things start going really fast up here. And it gets up to there, and maybe we are chasing or getting up to the glass right there. And by the end, make a really big change. And that would be about where the glass would overflow, because I'm at more of a depth.
It's rising so quickly.
And if I connected those, I get ooh, well, pretend that actually goes through the lines.
But that's it. So it's curved.
It's curved, yeah, and it's kind of flat, and then it gets steeper and steeper and steeper. And I could look at the same thing I did over here, where I'm just saying, hey, each of those arrows is how much the depth changed. It's just how much difference there was. And this was how long it took for it to change that much. And I could say, oh, this is how much depth divided by how long it took there. That's how fast the depth is changing. It's like a speed for the depth.
Right. So, but even though in this one it was exactly in between, in this one the curve, I mean, it's not an exact line in between.
Yeah, there was a nice straight line in between the 2 points there, but if I tried to draw that here, so we're doing this backhand, if I tried to draw that line here, it just sort of misses the actual shape of the curve, because it's not a straight line anymore.
But it gives you the sense of it.
Yeah, it gives you a pretty good idea of how fast it's actually changing. So, I mean, that's a nice idea. You can say, yeah, I like the straight line this time. I can draw a straight line this time. It's not quite as good, but it's an idea, right? It's an approximation. And we can do the Martini glass. Let's see. So that's going to be the green Martini. There we go. Same thing, right? Starts out with nothing in it. And then that first one, so let's see. Start out down here, and it makes a big jump. Right? So it may fill up a lot more than the water glass did. And then I start with that much water, and it makes a big jump, but not quite as big of a jump. So that's
Every time a little less.
every time a little less and a little less. I start from the same amount and a little less. I start from the same amount and whoops, and a little less, and actually so long, shorter, shorter, shorter. I'm trying to make them almost the same way I drew those, because it is basically what's happening.
And so you're getting that kind of starting point from the previous fill. Thinking about.
Yeah, I'm just drawing how much more water, how much more of the depth, how much deeper it was. There we go. And by the end over here, I have that much, and just a tiny little change, and almost nothing happens. If I connected those, I get this thing that sort of curves.
Opposite
way.
curving direction of the Erlenmeyer class.
Yeah, it's still going upwards, but it's slowing, right? It's getting slower, which is what you see, right? I just keep pouring at the end, and things are barely doing anything. So, yeah. And same thing, right? I could say, like, from here to there, that's how much the depth increased, and that's how long it took to do it. And if I draw the line that goes through those, oh, that's a terrible line. But you can, it's kind of close, right?
Yeah.
It's in that same general area, but because this thing is curving, it's really not the same as a straight line between those points.
Yeah.
It's real close.
Oh, fascinating. All right, I love that visual of the glasses filling at different speeds. So if we, as we're moving on to thinking about derivative, this rate of change, we could even draw out somehow from these graphs the rate of change of each one.
You could, yeah. So you could, so you would draw on how much water there is in each glass. But sometimes it's more interesting to know how is that changing, right? Because we were sort of looking at the shapes of these and saying, oh, I can see from the shape what's happening. This is green one's increasing slower and slower, red one's increasing faster and faster. Well, if that's what you really care about, why not just draw a picture of that, right? Yeah. So I could do that. Let's see, where am I going to do that at?
Can we make just pick one of them and
yeah, let's just
like the red or the green?
Let's pick the red one actually. And yeah, here we go. I'll stand up.
It's okay.
Yeah, all right. All right. Yeah. So what we're going to do is we're just going to look at the stuff we drew for the red one, and instead of going from, you know, here's where I was and then here's how much more, and draw a picture of that total, right? Because that's the total. That's the accumulated amount of water. I'm just going to draw how long that arrow is. I'm just going to draw how much more there was. So I'm going to, let's see. Let's really line these up as best we can. So let's pretend that actually lines up here and this lines up over there somewhere.
Okay.
I really want to draw the same things at the same place.
Well, or do you want to just copy the red curve over?
Yeah, that's a good idea. All right, so that's the red curve,
Okay.
roughly. And so I drew this. We started out here and I drew that tiny little arrow. And so what I'm gonna do is I'm just gonna draw a dot for that arrow. I'm just gonna say that's, however tall that is, that's just how much more water there was.
That was the change in that amount of time.
That was the change, yeah. And because that's starting from nothing at the bottom of the flask, that's also how much water there is in the flask, but just that once.
Yeah.
And the next time, so down here, I started from there and it went up a little bit. I'm just gonna draw, say that little bit. I've managed to draw my curve.
Very slow at the beginning.
Very slow at the beginning, yeah. So the, let's see, that dot should be on there. Okay. The arrow is so tiny you can no longer see it on there. And so then I made a...
Smaller than a dot.
Smaller than a dot, in fact, yeah. So I made a little bit of change, and that arrow, so that's this arrow right here, is how much more water there was.
I'm gonna...
Right. Yeah, something's not working on here.
Well, I'm just gonna zoom in, right? So,
Yeah.
as you're saying, so like this is kind of where that first dot was.
Uh-huh.
And the second part is this in our original graph, that was
Yeah.
the change. And now you're gonna make kind of that the dot, kind of the red percent.
Yeah, there you go.
Don't let me put words in your mouth though.
Okay, yeah,
So you're imagining
we're
that
taking-
change now.
Yeah, we're gonna take that little extra arrow that was added above the first dot. We're just gonna copy it down there, and we're just gonna draw how tall that arrow was.
Okay.
So that's what we're trying to draw in there.
So then this next one's gonna be a little more visible, right?
Yeah, okay, that's a good picture. So in the next one, there we go. So in the next one, I'm starting from that much, and I added that much more. But instead of drawing it right there, I'm just gonna draw it down here. I'm just gonna say that's,
Because we're trying to just capture the change.
yeah, we're just trying to capture just the amount that it changed. And then the next time I went from there up to there, and it changed by that much. And I'm just gonna draw a picture of how tall that arrow was. So something like that. And if I keep drawing that, the arrows kept getting bigger and bigger. They're not the same thing as the curve we already had.
But it's the same,
But it's the same
kind of
yeah.
curve.
It's the same information about the curve too. Yeah, and it is the same kind of curve. It's getting bigger and bigger, right? And so if I'm reading those, let's actually connect the lines here. If I'm reading these dots carefully, like that dot right there just tells me that this much more water got poured into the container. Or I gotta be careful, because I say this much more, it sounds like volume of water, right?
Right.
But it's not, this is where that's how much higher the level of the water
was.
got, right? Like from there to there. And so that just, whatever that number is, it just tells me that's the new additional height. That's the increase in height there.
And if we wanted to find the total height at that point, we'd have to add up all those changes of heights we had before.
Yeah, and so we'd have to do the accumulation thing and say, first I added that much, then I added that much, and then I added that much, and then I added that much, and then I added that much,
Yeah.
and add them all up together, and that'd give you the bit, plus that bit, plus that bit, plus that bit. Totally
Well,
up there.
I love that, because it's like, you know, starting with the original curve, we could figure out this rate of change curve, which is what you just did. Or starting with the rate of change curve, we could have figured out.
You could figure out that original by adding up the bits. Yeah.
It's to both directions.
Yeah, so you can do things in either way. You can add a bunch of little bits to get a total, or you can start with a total like we did down there and figure out all the little bits that you got to add up.
Oh, very nice.
Yeah.
Good. And then, do you have any particular kind of response you get from the students with this?
Usually when we do this particular video, there's where it gets very slow at the end.
Yeah.
They actually are they're, oh, never. But yeah, the connection that happens here is a surprise, I think, because there's a bunch of different things going on. There's the water getting poured, there's how deep the water is, and there's how much the depth has changed in each time That's a lot of different things to keep track of.
Especially interaction with the shape of the glass. And,
Yep, and yeah, there's so many different things to visualize and to try to keep in your mind.
Yeah.
And so really, I mean, it pushes you a lot, but that's when you figure stuff out too, right? It's like, oh, I've got 3 things. How do they all mean the same thing here?
What are the connections?
Yeah.
Oh, super nice. Well, thank you so much for
Yeah.
sharing that.
Thank you.
Oh, I appreciate your time. And now, maybe it's because we're filming at the end of the day, but the margarita glass makes me think you could think about if you were taking constant sips.
There you go, constant decrease.
Right.
in,
What would be
yeah.
the rate of that be? So
I like it.
we'll leave that for you to work on your own.
Do it for a wine glass.
Oh, nice. Yeah.
Curved shape.
One of their options is designing a glass, designing an ideal glass. So
Okay. Yeah.
for a different assignment.
Ideal for
Beverage of their
whatever.
choice.
Okay.
Yeah. Anyhow, so thanks again.